again, good morning, and welcome back to my YouTube channel. It's still Organetica Caroline. I'm Organetica Caroline, a graduate of Petroleum Engineering Technology from the Petroleum Training Institute from Delta State, Nigeria, and a postgraduate diploma student of the Abubakar Tafawa Balewa University, Bauchi State. So, it's the online science tutor. This channel is geared towards preparing secondary school students for their A-levels exams for WAEC, NECO, and JAM to be precise. And so for this journey today, we are going to be treating a topic in physics, because in this channel we treat the three major science calculation subjects. That's chemistry, physics, and mathematics. And also, we advocate strongly that every student should get their past question and answers. So this is the one for the physics. This is the physics series, so secondary school certificate examination, past question and answer physics. Alright, so we strongly recommend this because it would be a guide to you. So whenever you are studying, you have an idea of what is expected of you as a student from the syllabus, okay? Alright, so for those of us that have subscribed, I want to say a very big thank you. It's really been amazing. Thank you for making this journey an easy one for us. We are most grateful. And for those that are yet to subscribe, please, if you got value, don't hesitate to subscribe at the end of this video. Alright, so today we'll be looking at a very crucial topic in physics, and it's one of the topics that is going to be reflected very well in your certificate examination, because it's an aspect of physics that is actually a building block to those that will go into some form of engineering study that will demand the knowledge of thermodynamics, so thermo and every other thing that has to do with heat energy. So this morning we're going to be talking about heat energy. Okay, so heat energy. There are various aspects of heat energy that are actually captured in your syllabus, but for this very tutorial today, we'll be making emphasis on the calculation aspect of it. So there's a part of heat energy where you do the theoretical aspect, like what is heat energy? It's a form of energy, and that is highly dependent on temperature difference. And talk about the definition of temperature and all that, including the units of measurements and also the apparatus or equipment for measurement. So for temperature, for example, you deal with things like the thermometer, the various types of thermometer we have, and what they use in their measurement, like the property of that particular fluid or that substance that make it to become a thermometric substance. What I mean is, in looking at types of thermometer, you talk about liquid in glass thermometers. So oftentimes you hear mercury in glass for those that the thermometric liquid is mercury, and then you also see alcohol in glass for those that the thermometric liquid is alcohol. Then we have gas thermometers, we have the thermocouple, and all of that under the theoretical aspect of temperature. But that's not our focus for today. Our focus in this class is to be able to deal with the calculation aspects, and this became necessary for me because most students that have encountered in my lecturing journey always have issues with the calculations. They are not so much bothered about the theoretical aspects. Most of them will just like, okay, don't worry, I can read up the theoretical aspect myself in my textbook. What I really don't understand is the calculations that follow. So that's why this video is dealing with calculations in heat energy. So if you have a challenge with the theoretical aspect and you would need me to also make a video on that, please kindly state in the comment section below, and if I see the response, and the number of people that actually need it. I will also make a video on it. But for today, the emphasis is, like I said, is the calculations aspect of it. So at WAEC level, at WAEC, JAMB and NECO level, what we'll basically look at is things that has to do with calculations of linear expansivity, volume expansivity, area expansivity, and then you also calculate for quantity of heat, discharge, then you look at heat, latent heat of fusion, latent heat of vaporization, and the calculations that are entailed in all of that. Alright, so this morning, that's what we'll basically be doing. We'll be picking up questions from the past questions. So I'm picking up questions from the past questions for WAEC, and then we'll solve that. You see what you're expected to do in each question you are given. Okay. All right, so having established that, let's go straight to the calculations. All right, so the first thing we'll be calculating for is linear expansivity. Okay, linear expansivity. Now, anytime heat is applied to a substance, the temperature of the substance changes. Alright, so, and when the temperature of the substance changes, it causes certain effects. They are called the effect of heat energy. That's the effect of the application of heat energy. One of that includes that there will be a temperature change, and also that can affect the pressure of the substance. And then for some substances, we have thermionic emission. That's the emission of electrons from the surface of either the metal that is being heated. But one very particular effect of heat energy on a substance is that it causes an increase in its length. What I mean is this, and I'm giving this background knowledge because when we start calculating for linear expansivity, I want you to be able to picture with me, because it's actually an increase in length that we're solving for. Alright, so if, for example, I have water, let's assume this is a pot, and the pot contains some quantity of water. Okay, so this is my pot A, and then I applied heat energy. So this is a source of heat. Let's call this a Bunsen burner. Alright, as the substance is continuously heated, I don't expect these molecules of water to stay at this point they are. Okay? And the reason is simple. As more heat is introduced into this very particular substance, the heat energy increases the temperature of the molecules. So this is heating. Don't forget that from the heat source, I'm having conduction here. That's between the source of heat and the pot. There's conduction. And then between the molecules of the liquid, there's a convection current that is set up. And because of that, the molecules in the pot acquire greater kinetic energy because their temperature has increased. So they tend to now move more, and so they bombard the wall of this pot more. And because of the increase in their kinetic energy, you will expect that the molecules will extend to this point. That's also a basic analysis of Charles' law that says that as temperature increases, as the temperature of the given mass of gas or substance increases, there will be an increase in the volume of the substance. So this is the volume. So this is V1 at temperature 1, and this is V2 at temperature 2. Alright, so if this is occurring, I know that there is an increase in the volume. But for linear expansivity, we are not considering every other dimension of that particular substance. We are considering just the expansion in the length, that's linear. So for example, a straight line like this is linear. So we're just considering the length. And for linear expansivity, we say alpha, which is the symbol for linear expansivity, is equals to L2 minus L1 over L1 bracket theta 2 minus theta 1, where alpha is equals to linear expansivity, then L2 is equals to the final length of substance, L1 is equals to the original or initial length, and then theta 2 is equals to the final temperature and theta 1 is equals to the initial temperature. Okay, so we said the linear expansivity of the substance, the formula to calculate for it is L2 minus L1 over L1 bracket theta 2 minus theta 1. This can also be written as L2 minus L1. Whenever I do a subtraction of L2 minus L1, what it's going to basically give me is the increase in length or the extension. So that means that there are questions where I may not be given outrightly that the final length of the substance is this, the original length is this, and at this temperature and this temperature, but I may be given the increase in length. So if you are given increase in length, I don't want you to get it confused and be saying, oh, they didn't give L2. No. What they already gave you by giving you increase in length is that they have captured L2 minus L1. So what you are now expected to do is to just put extension, that's E, or increase in length. So this can also be written as increase in length over L0, which is the original length, bracket degree T. Don't forget that data means a changing. So there are also questions that they may give me the temperature rise. So my question may not state that a substance at temperature 10 degrees, for example, was heated until its temperature became 15 degrees. You know, in that case, my theta 2 minus theta 1, which is 15 minus 10, is going to give me 10. It's going to give me 5 degrees Celsius. But if my question states that a particular substance was heated and a temperature rise of 5 degrees Celsius was observed, I know that they have already given me data T. So in that case, instead of using this equation 1, let's say this is 1 and this is 2. So in that case, I'm going to have to use equation 2. So it's not compulsory that they are going to give you L2, L1, theta 2, theta 1. No. The only thing I know that they would most surely give you is your L1, because I need to know the original length the object was before it was heated to get an increase in length. That over time, I've studied the pattern of questions being asked. That over time is the question I have seen play out. Okay, all right, so right now we're going to take some questions from the past question on that linear expansivity and then solve. So this is 2009, question number 18. 2009 question 18. So our question says a rod A rod of initial length 2 meters at a temperature of 25 degrees Celsius is heated to 80 degrees Celsius. Calculate the increase in length of the rod if its linear expansivity is 4.0 times 10 raised to the power minus 3. Just something to, as a pointer. Oftentimes, I already made a video on that the way science questions are asked oftentimes require that you do a change of formula. So, every time when a question is given, the first thing I want you to do is to write out the data you are given. In that way, when you now write out your formula, you just impute the data. But if what you are given demands that you make a conversion, the next thing you will now do after writing out your data is to do the conversion even during the data while you are writing down the data, so that you don't forget and impute and solve directly. Those are just some ways that most science students miss some marks without knowing. Okay, so for this our question, data given 1, L1 is equals to 2 meter, theta 1 25, theta 2 theta 2 80, and then linear expansivity so I'll write out my formula. L2 minus L1 over L1 bracket theta 2 minus theta 1. Okay, so 4.0 times 10 raised to the power minus 3 should be equals to L2 minus L1 over L1. Okay, so wherever I have L1, I'm going to impute my data directly. Over L1 is 2 meter, 2 bracket 80 minus 25. So 80 minus 25 should give us 55. I can cross multiply here. Then I have L2 minus 2 should be equals to 2 bracket 55 into the bracket of 4.0 times 10 raised to the power minus 3. Okay, so if you do this with your calculator, what you basically get would be L2 will be L2 minus L1 therefore L2 will be equals to 2 plus 0.44 meters. Alright. Okay, so you just saw the way we worked on it. So I wrote out the data and started imputing for all of our values. You saw that when I got to this point, I just did this over 1, but whatever, if any number is divided by 1, it's still going to be the number. But I did that so that I can achieve unity, so they can look alike. Since this is under a division sign, I can do that. so that in cross multiplying, I now have L2 minus 2 multiplying 1, which is still the same number, then the value for linear expansivity multiplying L2, L1 bracket change in temperature. So solving that, we got that L2 minus 2 is equal to 0.44 meter, and so therefore L2 will now be, if these two crosses the equality sign, it becomes positive, that's why it becomes plus 2, and then the final answer becomes 2.44. Have you understood what we did? And what this question also just showed to us is that there are times when in linear expansivity, you may not just be solving for the linear expansivity. So a question can state that you solve for the temperature rise. And don't forget, at WAEC level, most of the things you'll be doing, they'll be for just one unknown. So if you are given a question to solve for temperature rise, for example, you are going to be given L2, L1, and then the linear expansivity. But still solve more questions under linear expansivity to broaden your knowledge. Expansivity of brass between 27 degrees and 100 degrees, this amount. What is this linear expansivity? Something I forgot to mention, thankfully this question had to bring it up, is that there are some times when your question is going to demand that you understand the basic relationship between a linear line, then area and volume. So in linear expansivity, when we consider just the increase in length, what we solve for is linear expansivity. So that's just this sign. So this is for linear. And then for area, beta, area expansivity. And then we have volume or cubic expansivity. But 1 beta is equals to 2 linear, and 1 y is equals to 3 linear. Okay? So because in area, what I'm considering is length times breadth. So it's 2 times of length. That's why area expansivity is 1 beta, which is 1 area expansivity, is equals to 2 times linear expansivity. And 1 volume is also known as cubic expansivity. So that if your question states that the cubic expansivity of a given mass of substance or of a given substance, you shouldn't be thinking that they don't know what they are talking about. So they can either use cubic or area, whichever one is the same thing, it's one and the same thing. So if they say 1 volume, I want you to know that 1 volume, we are looking at length times breadth times height. So that's 3L. That's why volume expansivity is 3 times linear expansivity. So my question now says that this is the volume expansivity. If volume expansivity is this, what will be linear? Recall that 1 volume is equals to 3 linear. Since I know that 1 of the volume is equals to 3 linear expansivity, so whatever value I'm given, I'll just divide it by 3. Okay, all right, so simple and straightforward. If you are given volume expansivity and you are asked what is its equivalent in linear, you will divide by 3, because 1 volume expansivity is equals to 3 of linear expansivity. And so if you are also given area expansivity of a certain metal, for example, and you are asked to calculate for the linear expansivity, you will divide by 2. What we are basically using is the relationship between them, that 1 of area expansivity is equals to 2 times the linear expansivity, and 1 volume rather, is equals to 3 times linear expansivity. So that way you can easily get your answer. Okay, so we'll solve one more question, and that will be all for linear expansivity. But if you have any other question, feel free to drop it in the comment section below. Alright, so our question says, a wire of length 2 meters long is heated from a temperature of 5 degrees Celsius to a temperature of 55 degrees Celsius. If the change in length is 0.02 meter, calculate the linear expansivity of the wire. So this question just reflected what I said, that there are times when they will not give you the final length L2, but they'll give you increase in length. If increase in length has been captured, please don't go and do a subtraction again. It simply means that they are giving you extension, so you solve with the formula 2 that we highlighted earlier. Okay, so first thing first, we'll write out our data to guide us. Okay, so L1 equals to 2 meters, theta 1 equals to 5 centigrade, theta 2 is equals to 55 degrees Celsius, and then extension E is equals to 0.020 meter. Linear expansivity is equals to L2 minus L1 over L1 bracket theta 2 minus theta 1, or extension over L1 bracket theta 2 minus theta 1. Alpha will be equals to, our extension was given as 0.020 meters over L1 was given as 2 meters, so the bracket of temperature rise 55 minus 5. This should give us 0.020 over 2 bracket 50. Don't forget 2 times 50 should give us 100. So our answer would be 2.0 times 10 raised to the power minus 6. Okay. Alright, so that will be all for linear expansivity. But then don't forget that this is in degree C. Length will cancel at length, so my final SI unit will be per degree Kelvin. So that's for the SI unit. Alright, I hope you've been able to get value today in today's lesson. If you have any other questions that borders on linear expansivity, please don't forget to drop it in the comment section below. And for our next class, we're looking at the thermometer. So look at the upper limit and lower limit, and calculations that border on upper limit and lower limit of the thermometer and the interval. So please don't forget to subscribe to this channel, like this channel, and share with others. Thank you for staying with us till the end, and don't forget to come back. So see you in my next video.